So I have two affiliations with the University of California, Berkeley, and with one of Berkeley National Lab and the Applied Numerical Algorithms group. So all this starts quite a while ago with making this plot up, and the extension of this plot up probably about 8 or 9 years ago now. These are old XT4 machines, and at first I was getting funny scaling behavior, BPM type hyperbolic code on a particular machine. This is when Jaguar was quite new. So I started turning things off. So I started turning off I started turning off roller bounds, I started turning off. I made the grid simpler, and I made the problem simpler, and I took out all the NPI, and I took out all the synchronizations, then I took out all the different physics. And I was left with, I was doing the same patch, doing the same physics, on the same box, on every processor, on the entire machine. And I'm still getting this kind of time performance. This is an embarrassingly parallel PPM benchmark code. And you'll notice that you're getting these, this is the different processes you're talking to. And this is how long it's taking to do, going through a certain number of boxes and do the calculation. So you notice that we have this kind of wide band, and you notice you also have these big spikes. And these big spikes are the result of persistent DRAM failures on the machine that don't stop your job from running. So what's happening is that your memory, I'm not sure if you know how much your computers are made up, but your bytes or your words aren't on individual DRAM chips. Your memory is banked. So each bit is sitting on a different DRAM chip. And that gives you lots of bandwidth. So as you load a word, every DRAM chip can grab it, put it on the bus, and off it goes. So there's your big bandwidth, and that's all for the same latency. But if one of the DRAMs goes bonk, it's still going to load up, it's still going to come in. Since it's only a 1-bit error, you have an ECC code up near the processor at the end of the load stage, where it can detect the 1-bit error, and it does a little logic, and it hands you back the byte. So you never see that this is a calling, but what you'll see is I'm consistently accessing that piece of memory, and it's consistently going slow. So the particular set of loads for a particular machine, if it's got a bit in that 1-bit of bad DRAM, it just takes a lot longer to show up. So you integrate this enough times, and you will see that there's tens of seconds getting lost in that load time. So this is a property of the machine meeting its contract. The machine has to stay up, it has to have a lifetime, the job didn't die, code went through, and all you saw on your timetable, if you're going to look at your plot, you'd say NPI reduce. It was all lost in NPI reduce. And of course, what you're really having is ragged entry. Everyone's showing up, someone's arriving to the reduce way too late. So it looks like synchronization time problems. So, you go off and write, an NPI reduce benchmark. You see that it takes, microseconds on the machine down to, or a little bit less, maybe 30 or 40 microseconds. So that wasn't done. So, eventually you go pouring through logs and you find a bad node and you tell the system base and they go and replace it and they swap that out. So now before you run a job on a Craig machine, they run my benchmark and they go look for this property. And then, so just before your batch job starts out, my node runs. And it looks for this behavior and then it'll actually schedule your job. And if it sees this, it takes that node out and notifies the system base. So, okay, so maybe we don't have all these spikes. So we take the spikes out. What does the data look like? So now this is a histogram where the height is how many processors took that one. And you can see for various versions of the chip architecture and various versions of the operating system, this is back when we had Catamaran, you can see that we're still getting a spread, and the spread is still fairly large. And all of these guys have to wait for this guy to arrive at the end. So there's still maybe a significant percentage of time spent waiting for the last straggler. And you can see this trimodal problem when you get into compute no Linux and compute no Linux on Franklin versus Jaguar. These are two DOE-based machines. Things move a little bit. I would like what Catamaran was doing. So some of what this bumpiness is not the hardware. It's something to do with how pages are assigned, has to do with stuff about how processes are lined out memory, but it has to do with your programming stack. So, what does that mean for everybody? So, before you think that's bad, he'll tell you that it's going to get worse. So what's really going to expect in the future is that all the major, machine vendors are promising us, more of the same. We're trying to do, benchmarking on new algorithms in Jim Demel's group. We're doing, a new version of communication avoiding WISE routines or LA-PAC routines. We have this kind of cold start, or the machine's been running too long problem. What's really going on is that turbo boost is going on and going off. The processor is detecting a high load, a high thermal condition, and is downclocking certain cores. So in order to maintain, the mean time between failure for the processor, and most processors are sold in the commercial market. In the commercial market, CPU usage is very bursty. There's a human in the loop. You look at your screen for a little while, or you touch a key, or you wait for I/O to happen, and you're not really, most processors are sold in an environment where usage is bursty, and so they never really bound clocks. But if you run it long enough, eventually the cores are getting downclocked. And, AMD has this, the chipset that's next to your chipset, so your memory bus has this going on, the chips that go to your DRAM have this going on, your DRAMs have this process going on. And then your interconnect, so your on-chip interconnect can do, downclocking. So if the interconnect if QPR is going too slow on the mic, then it's going to start downclocking your cores. You have more fiber in between your processors than you're usually using at any given time. So there's some dark fiber that's sitting in the machine. Eventually you run out of dark fiber because as fiber dies, it switches on some of the dark fiber. Eventually some of your dark fiber, so you start losing fiber links. So it starts multiplexing its data onto the less and less fiber. So over the course of the machine's life, you'll have the same latency, but it has to reuse links to get the bandwidth correct. So you'll see that certain cores just can't talk to each other as fast as they used to. And you can't really predict that. And sometimes you lose nodes completely in your link. But what it'll do is it'll do a rewrite. And a rewrite takes a little bit longer, and you never know this is occurring. And we're getting into a world now where we're getting dark/dim silicon. So what this really has to do with, I can put I reached the point now where I reached the utilization wall. The utilization wall says that I can put all the silicon on the chip based on the size of the nanometer technology I have, but I can't afford to power all of it at once. I put all the silicon on that die and powered it all. I would have a mean time between failure for that chip. Its shelf life would be about measured in months. So you don't do that. So you have this kind of coming four horsemen of the utilization apocalypse. So you currently have multi-core chips now where, a lot of the real estate of the chip couldn't be fast, hot things like ALUs or FPs or things like that. It would make vector units, which are much more energy efficient. And really, if you kind of do a X-ray, if you do an infrared image of a chip at small scale, you realize most of the L3 is sitting there rather dim. It's not really cycling much because you're hitting areas all the time. And it's kind of moving things around in the L3 cache to keep the heat moving around. But you're going to see more of what that previous slide had. You're going to see more, these are homogeneous architectures. You haven't been technically given a heterogeneous machine yet, so you're not given a GPU. The reality is we've had heterogeneous machines for 5 to 7 years now, and you're going to see just more of it. And my conjecture is that all fault tolerance is going to look something like variable performance. So we are a boutique, programming environment people group. They can't cater to us. We have to basically ride on the back of a much larger commodity market. And in the commodity market, if you think, the previous context for this was soft errors. Everyone was telling us 5 years ago, be ready for soft errors. Algorithms that can resist the problem of, I'm going to do a floating point operation wrong and just give you the wrong answer. And you have to somehow detect this problem. And all of us said, you got to be out of your freaking mind. But they said, algorithmic fault tolerance is much cheaper energy-wise than having the processor do it. I said, there's also an economic problem. If you go off and sell chips to people in which the Excel spreadsheet just decides to change a number, I'm going to have a hard time selling that processor in the commodity market. Or if it accidentally leaks my password, or if it accidentally opens a port on me. All these kinds of soft errors that are not detected create an entire crapstorm for anybody in private industry. And they have the billions and trillions of dollars to spend, not us. And that would be on the cover of PC World for months if this was occurring. I remember the little floating point bug that happened that one time, and everyone recalls it, right? That one little bad processing in the Intel generation. So, what we're talking about with software is getting through is much bigger than Y2K. Everyone collectively lost their crap over Y2K. So, that's not going to happen. So, they are going to put in the extra bit level environment in order to detect these errors. Much more of the errors are going to be detected. The kind of errors you're going to get are not what you probably think. But I can't do it with any more money. So, the last option that I have available is we have variable performance for how long it takes to do an operation. So it's not really stochastic, but it's going to have heterogeneity in the execution time. So no hardware performance, we're probably going to have the same or even better soft error grabbing and detecting that we enjoy today. This is not set by us. How reliable a processor is set by the reliability of the dominant operating systems that are available today. So if you go to a hardware vendor, and you're talking to the guys who talk to us in our meetings, you go to the much bigger meetings, and you see that there's a graph for how reliable Windows is, and there's a graph for how reliable the current generation of processors are without having faults. As long as the hardware faults at a level below the operating system faults, you can sell that chip. If your chip goes above that, I can't sell that chip. That's this right here. If the current Samsung ARM Cortex processor starts generating faults faster than greater than what iOS does, then Apple will go find a new vendor. So Samsung will push down their error rate until it falls below the operating system is expected to run on. This has nothing to do with us, right? That's the big market. So what you're going to see is, how do you get a benchmark around a certain time? Most of the benchmarks are insensitive to having little variabilities in performance, right? So you're going to get averaged sense fast processing, but you're not going to get these soft faults trickling up into your applications. So what's it really going to do? Well, how much does it cost to correct an error, and how much does it cost to detect an error? Detecting an error costs a lot less in terms of silicon. It allocates anywhere between 20 to 40% of your silicon on die to have a fairly robust soft error detection mechanism. So you can detect the soft error, and you do what the other generation of machines will be doing, which is everyone's doing these problems where people do fault tolerant GMRS, people are doing fault tolerant Krylov notices, people are writing fault tolerant ways of doing particle integrations and things like that, and that's all based on the idea that your loads and stores are going to be faulty. But really, your data path is almost the most reliable mode that's going to be in your machine. The most common thing is a latching error, in which case it's not a 1 or 2-bit error, it's the entire number becomes random. So, it's really hard to detect that on your own. So, you're not going to. So, what's going to happen? Cheap faults are going to be corrected. So, you're going to have ECC or you're going to have SEDC, you're going to have double or single bit correction. And that's just based on, because memory is banked, you're going to have this problem of occasionally chips die, and you're going to replace them based on whatever the maintenance schedule for the machine is. So, you all get the email from the center saying, we're going down for scheduled maintenance. That means right now there are probably about 45 to 500 chips on the machine or components of the machine that are misbehaving. They're not executing correctly, but the machine is still up. Those nodes are still scheduled. You're still using them. And then they go into the weekend and they start doing the chip pulling, and they have a bucket of chips that go with that machine. You get a whole bunch of spares, but you got a hot slapper, right? The machine goes down. So that's what happens when the various your supercomputers or the ones that DOEs. So that's what they're doing. But things like retry and all that, they're actually going to be pushing that down into the memory system. So you're going to start getting logic in the memory to do that before the chip even sees it. So there's an extra layer of silicon underneath the DRAMs now. They're going to start putting more logic in there. So, and I can, that's embarrassingly parallel and very low power. So, the bad news is that, it's okay for my machine to have a, mean time between interrupt below my operating system, and that means I stay up for maybe 4 or 5 months, typically, before I get the little blue icon, the Apple icon on my laptop. So my chip's going to be somewhere around, 5 to 8 months between it just has a kernel panic, and just takes the machine down. So I need to reboot anyways. I have a lot of software I have to update on. That's okay. It comes back pretty quickly. We had to build a machine that has the order of 100,000 of these put together. So if you take, mean time to interrupt for typical batch job on Blue Gene right now is about 6 days. So if you have a batch job that runs significantly longer than 6 days on something like a Blue Gene P, then, you probably have to come back for your checkpoint. At the future Exascale machine, my estimates are you're going to get about 2 hours. So, I can move this up and down by a factor of 5, really, based on whatever hardware trends I can make assumptions about, and how much they try to squeeze my energy budget down. Squeezing my energy budget down a little bit to move this number by at least a factor of 2. So, checkpointing and restarting the disk is not really going to be an option. But we are going to have the fact that, there's a whole bunch of things that could go wrong in the process. The most likely thing you're going to see, they're going to promote all these other errors up to kernel panic. So I'll describe what kernel panic could be like in a minute. But the primary recovery has to be something like localized recovery of the compute context. So what can we reasonably expect vendors to try doing about this? So the next generation, because the machine has this property, and because I'm going to put it on the floor and I'm going to ask for a lot of money, the vendor has to do some level of providing a way of recovering from the fact that I can't get even through several time steps before my job goes down. So you're probably going to have something like the OS is going to, usually you have these things called MCA registers. Intel has the MCA registers. So that's where it goes and sets, the hardware detects an error that's not recoverable. It sets bits in the MCA register. So the one level up in the OS before it goes through the fetch and decode phase for your next operand. Somewhere in the fetch and decode phase, it checks the MCA register to see if something like had sometime recently. And it can send, and it says, do I have a signal handler that's going to do something about this? So currently, most machines are shipped with no handler. So the kernel doesn't, so then it's going to execute its instruction that says, take the node down. So, but the OS should have the option of saying, I can do something a little smarter than killing the job, if I know what kind of bit got set. So if it set the bit that said, your ALU is gone bunk. Well, my ALU is, I need that for doing things like computing a branch or calculating an address to do a jump. So I have to have kind of a separate ALU that's normally powered off, that gets powered up to handle if I want to do process migration. So if the one level up the stack is process migration, you can take all the pages, you have to move them to another node, so you need to swap nodes. But I tell MPI, I moved, I was at this NIC address, now I'm at this NIC address, so you have to know that's occurring. If there's messages in flight, make sure you grab them in the buffer and send them off to the next machine. And then in that model, you never know this has happened, right? That's where the OS has handled it. So there's people at our lab who are working on kind of OS, checkpoint, migrate, restart. But really, some people say that, if I have some domain-specific knowledge about what's really can go on there, or I can selectively say, that's a really expensive operation, doing all that style move. And everyone else is sitting at whatever the next barrier operation in your code is. Or they're rapidly running down a DAG tree, and eventually, you're the critical path. Whatever parts of your tree that you schedule on this guy are your critical path for getting finished. So maybe you can do something smarter, right? So if at the next level up, say you're running in a runtime system, say you're on top of Churn, or your Swift, or your Parallax, well, they know a lot more about the state of your code. They know a little bit better about how I could recover. So they intercept this, say, I'm not going to let the OS do it. I have something I can do it smarter. So I'm going to register something in that section. And occasionally, say say you're doing the load balancers running or the scheduler is running, and you can't really, there's parts even in the runtime system that really couldn't recover from their own errors. So then for that time, you unhook yourself from the register, then you let the OS handle it again. And then as soon as you can possibly do it, you put yourself back in. So you can, different levels of the stack, you can say, I can do something smarter right here. So you can go all the way up into the library code. So say a library code knows that, compute the residual. And say GMRes is resistant to the fact that occasionally you get the residual grossly wrong. So if I say, during this, from here to here where I'm computing the residual, I'm going to turn off even the runtime control. I'm going to say I'm smart enough at my application level that I can even tolerate this going horribly wrong because I'm resistant at the application level. How much does that buy you? I don't know. I don't think it's a hell of a lot. I've seen what it looks like when what people are doing is they're doing single bit or double bit errors in GMRes. Well, that's not the kind of error you're going to get. You're going to get the fact that the floating point unit or a control logic went wrong. Like the instruction comes in, it was supposed to be a branch not equal, it becomes a whole other instruction. It becomes, long jump. The code just walks off the end of the universe. And if you've told the OS not to handle this, and it goes and executes a long jump and does a segfault, well, now you've told the OS not to migrate you. Now your node is actually going to go down. So I think there's very few people that are going to try playing in this world. And I think it's kind of academic. I think the only really robust option is the runtime system and the operating system. Your application doesn't have, you're not really sat down and thought about the kind of things that go wrong in a CPU when you really drop the voltage low. So, we're going to go into anything else for that? Alright, so I also have this, the machine is getting more, is heterogeneous, it's going to get more heterogeneous. You also have heterogeneity coming from the other side. The other algorithms are getting more heterogeneous. You get a high rate of stencils, your stencils are certain you can cut off. You also have, everyone wants to do hybrid schemes these days. Multi-scale, multi-model, adaptive resolution, all create situations where it's difficult to know how long something's going to take to execute. I can't statically figure it out. So, the answer is going to be some kind of, Also, this kind of jittering I showed you before, the histogram is not just OS jitter. This is a typical OS jitter benchmark. You can see how tight this tolerance is. So there's tons of other things that are going on all the way up the binary execution stack that's causing this kind of variability. But how much should I do? What's the quantization in the resilience in your runtime system that has to absorb this? And the clue is somewhere in those histograms I showed earlier. Now, if I make the bins too small, everything drops to points on the line. If the bins are too big, I just get one bump. Right? So somewhere in there is a granularity that's hidden, and suddenly that structure pops out. So when structure pops out, that's telling you something about what kind of granularity do you have to go to observe. Numerically, am I already out of power? No. Alright, I think we're back up. So this is just a trend. These are the 1 petaflop machines at 200 terabytes, 20 petaflop machines at 1 petabyte. You can see where we're going. The memory is not scaling like the flops. And as a result, we need much higher fidelity simulations with only a very modest or meager increase in the amount of memory we have on my machines. So how do you get there? So adaptive mesh schemes are part of the formula. I call this algorithmic compression. I compressed the data before I even went into the PDE. So I've compressed the representation. You can also do compression afterwards. People have compressed sparse row where it's not, the C here is supposed to be compressed. There's compressed sparse row. So you do something like difference coding where the next number after me in the matrix is probably around the same order of magnitude as the last number. So I just do delta coding. So I don't actually store out whole numbers and bring back whole numbers. I keep track of the things that are going out in bunches. I keep the magnitude in one number, and all the rest is delta coding. So we use delta coding in lots of other places. We just haven't used it in scientific computing. And then it's high-order methods. You really have to push up the fidelity per byte. Having high-order methods means less memory, but lots of flops. That's what I'm going to be doing. So this picture up there. This is a hypothetical exascale node. So you have about 10 teraflops. 10 teraflops out of 100,000 of these put together. There's your exaflop machine. But you can see that I need arithmetic intensities up around this scale with vector instructions and, maybe some fusing in order to kind of get machines that run them. Most of our algorithms right now are around here. So even if I did all the fancy computer science you can think of, I basically hit the bandwidth limit. So you're not, your algorithm tells you where you are in this direction. And, all your fancy computer science is this direction. So if you're not over here, you're already out of the game. Right? If I have an arithmetic intensity algorithm, this is a property of your math. Now, technically I can have an arithmetic intensity algorithm that's 2, but it executes like it's a quarter because I use temporaries, I don't use my cache as well. So even if you do everything perfectly, a 7-point stencil, gradient calculation lives around here. So you're never going to really get over 2 teraflop on a node. So you need much more intense algorithms. Oh, but in order to, if you see the stack graph, if I have the algorithm that lives here, I do the stack graph, and here's naive, it's here, and then I do all the OMP I could do, it gets to here. Then I'm going to do prefetch, I get to here. Okay, now I'm going to do, I'm going to reorder, I'm going to do tiling to do this thing better, I get to here. This is a hard, slow march up. I think I've finally gotten a multi-grid that technically lives around here, up somewhere around here, on good current machines. So it's tough to push yourself much past the last few stacks. It takes about 25 or 30 different code transformation optimizations to actually hit your stream limit. Well, you're dropping logarithmic here, right? If I drop down even to there, now I'm only getting, now I'm below the current, right? So I'm not